Hello everyone and welcome to your lesson of physics. In this video today, I'm going to solve some of the past paper questions from the topic light. So primarily, I'll be solving the questions from the topic reflection, refraction, and also critical angle and Toronto reflection of light. And the questions regarding the lenses, I'll be solving in another video. So this one is primarily for the first part, only light. Now for the lenses, and most of the questions we are dealing with consist of the diagrams. They might be diagrams of reflection as well as refraction and some total reflection as well. So we'll be starting with it. Here we have the first question. It reads, figure 9.1 shows a very large plane mirror inclined at 45 degrees to the horizontal beneath a pattern on a high ceiling of a hall. And there you can see as well, we have uh, we have the ray of light R and ray of light S, which is striking at the mirror, and the mirror is placed at an angle of 45 degrees with the horizontal. Alright, let's skip to the first part. First part says, on figure 9.1, continue the rays R and S after they strike the mirror. So we all know as the rays strike the mirror, they'll undergo the process of total internal they'll undergo reflection. So what we have to do is we need to complete the path of the rays as they're reflected. So in order to show the reflected rays, the very first thing is you draw the normal line. So normal line, first of all, is drawn at the point of incidence. Here we have one point of incidence we have here, and the other point of incidence we have here. So we'll be drawing a normal line at the point of incidence, and that line should be perpendicular to the surface. So all right, and these two lines are represented by a dotted line, so we'll make this one dotted. All right, so let's assume that these two lines are normal lines and they are at 90 degrees with respect to the surface. And after you have drawn the normal line, the next thing is to draw the reflected rays. Like the first one, the ray R, it would be reflected at the very same angle as of the incident angle. So we'll reflect it on the other side of the incident ray, and we'll ensure that the angle of reflection equals to the angle of incidence. So basically, so this one is your angle of incidence, and when we're trying to reflect this ray, we reflect it in such a way that angle of incidence should equal the angle of reflection. So alright, so these are the two reflected rays, and I've just tried to ensure that the angle of incidence should equal the angle of reflection. But when you do it you would be doing on the sheet of paper, you can take the assistance from the protractor as well, just to ensure that these two angle of incidence should equal the angle of reflection for both the rays. And then we have the next part too. On figure 9.1, show how these rays are used to locate the image of C and mark and label the position of this image with the letter I. So once you have drawn the reflected rays, it would be very easy to locate the position of the image. All you have to do is to extend these rays, the reflected rays, just extend these rays backward. So once you extend these rays backward, they'll be looking something like this. So yeah, I'm going to extend them with a red line. So in the same direction, from the same point, we just extend them backward, and then we try to ensure that all the rays or any ray that we extend backward or behind the mirror has to be represented by a dotted line. So this one was a point of intersection, and that would be representing the position of the image, and we have to mark it with the letter I. And it would be totally accurate, very much accurate once you're doing with the help of a ruler and with the help of a protractor, because the previous case, once you were drawing the angle of reflection, and you were drawing the reflected rays, that also plays a role in determining the position of the image, because the position of the image would be accurate only if the reflected rays were drawn correctly. And once done with the help of a ruler and with the protractor, it would be totally fine. Then we move on to the next part, state two characteristics of this image. Well, so we have to represent two characteristics of the image that is formed by a mirror, all right, with the help of a plane mirror. So first of all, this image is image is virtual, and the other one you can write is image is upright. All right, so these two properties are the properties of any image that is formed by a mirror. It is always virtual, and we differentiate virtual image from a real image in such a way that virtual image is an image that cannot be projected on a screen. The rays of light are not actually intersecting, rather we extend the rays backward and we make them intersect. And upright means if the object was having an orientation like this, then the image would also be in this orientation. But if the image is something like this, that would imply that the image is inverted. So then the next part is suggests how the mirror helps visitor to the hall to see the pattern of on the ceiling. So mirror is placed at an angle, at 45 degrees angle, and we place the mirror at this angle, and the reason would be because if the person has to take a look at the pattern of the ceiling, in normal case, if there is no mirror, the person would have to like see all the way up. So if this is this is the ceiling, and the person is standing here, and this person wants to see there's some pattern on the ceiling, this person wants to see pattern on the ceiling, he has to look straight up. All right, but in this case, once you have placed the mirror at an angle, so let's say you place the mirror at a 45 degrees angle, so what would happen is the pattern of the rays from the ceiling would be reflected by the mirror, and they would enter the eyes of the person, and the person would be able to see the pattern of the ceiling without looking straight up. So what you can write here is seeing the pattern without having to look up. I mean, if he looks up, obviously he can see, but he does not need to look up to see the pattern. All right, everyone, let's move on to the next question. That is also from the topic uh, image diagram for a plane mirror. So figure 10.1 shows two rays from an object that is placed in front of the plane mirror. All right, so what you can see is the object is in the form of a dot, in the form of a point. We call it a point object. All right, so sometimes the object is represented in its actual shape in front of the plane mirrors, and sometimes the object is just represented by a dot, and that is called a point object. So part 1 says, on figure 10.1, draw the two reflected rays and locate the position of the image. So what we are given with is the object. All right, we are provided with the object, and the other thing that we are provided are incident rays. Right, so in some of the diagrams of a plane mirror, you're just provided with the object, and you just need to draw the position and the location of the image. But in this one, we are provided with the incident rays as well. All right, so the very first thing is we locate the point of incidence. Point of incidence are the points where the rays are striking the mirror, in this case the mirror. Then we draw a normal line to those point of incidence. So the first one would be like some place over here. Yeah, and then the second one, we draw the second one as well, and that one would be some place over here. It must be perpendicular to the surface. In this case, the surface is mirror, and secondly, it must be passing to the point of incidence. And these lines are represented by a dotted line. So let's make them dotted lines. All right, so these are the normal lines. The next thing that you have to do is you have to draw the reflected rays. All right, so first we draw the reflected ray in such a way that the angle of incidence should equal the angle of reflection. So for the first one, you can call this ray like A and this ray B. So for ray A and B, the angle of incidence should equal the angle of reflection. So I'll be trying to draw these rays now. So we start from here for the first one, and we'll just try to ensure that the angles are same. This is a key thing here. And to ensure, if you want to really be certain with it, you can draw or you can measure the angle with the help of a protractor, just to ensure that these angles are same. So here's the first one, reflected ray, and I'm going to draw the second one as well from the second point of incidence, and it would be like some place over here. Yeah. All right, so I'm just giving you an indication. Once you're doing with the help of a protractor, with the help of a ruler, it would be as accurate as it has to be. And second thing, you have to draw the arrows as well. These arrows are showing that these are reflected rays as they're moving away from the mirror. So we have drawn the two reflected rays, and now we need to locate the position of the image. In order to locate the position of the image, what we can do is we can extend these rays backward, because uh, on this side these rays are not going to intersect, because these rays are diverging, they're moving away from each other. So these rays would not be intersecting uh, on this side. So what I can do is I'm going to extend these rays backward. And when we extend these rays, we just make sure that the extended rays are represented by a dotted line. So I'll be just drawing the lines first, and then we can make them dotted as well. So here's the first one, and then let us draw the second one as well. Yeah, and here's the second one, and let us make these rays dotted. So any ray at the back side of the mirror, behind the mirror, they are always represented by a dotted line. All right, and the next thing is we find the point of intersection. So the point of intersection in this case is over here. We draw a dot here, pretty much the same size as of the object, and that would be the position of the image. We can write image here. Apart from its position, state one characteristic of the image. So a characteristic in terms of the position would have been the image is on the other side of the mirror with respect to the object. Another characteristic would have been image and object are equidistant from the mirror. So apart from these two characteristics which are related to the position, we can also say that the image is virtual. Matter of fact, any image formed by the plane mirror is virtual because the rays were actually not intersecting. We just extended the rays backward and we made them intersect. So we can write here image is virtual. All right, everyone. So here we have the next question. And in this one, first I'm going to solve this one part. Figure 6.1 shows a plane mirror used by a dentist to see the point labeled X on the tooth. Then we have the figure 6.1. Part 1 says mark the position of the image X formed by the mirror. So this is basically the case in which you're provided with the object in front of the mirror and the eye is also given. So but we'll be dealing with that in the next part. In the first part only, we have to mention the position of the image formed by the mirror. So you see, we know from the properties of the image formed by the mirror that image is equidistant from the mirror and it is in the same line with respect to the object. So all right, so if you want to extend the mirror as well, you can in the same direction. If you want to extend the mirror, you can, to give you a better indication. Like this is the line in which the mirror is placed. So, alright, so you can call it image or you want to call it X prime, X dash, whatever. That would be your image. So I can just write I here. And mathematically, I can show that this distance equals this one by drawing two crosses. All right, it represents that the distance, these two lines are equal in length. All right, so now in the second part, let's take a look at the part 2. Draw a ray of light from X to show how the dentist can see the tooth. All right, draw a ray of light. So what we have to do is, this is basically a case when the object NI is given. So all we have to do is, once you have located the image, then you draw a ray from the image towards the eye. So generally we draw two rays, but in this one they have asked us to draw a single ray. Draw a ray of light, all right, from X to show how the dentist can see the tooth. All right. So first of all, we join the image to the eye like this. And once we are done with it, we ensure that the back side of the mirror, or the line at the back side of the mirror, has to be a dotted line. All right, because that ray does not exist in reality, it's just an extension. And finally, the last step is to join the object, which is a point X, with the point of incidence on the mirror. So over here, then we draw the arrows as well, and the arrows are away from the object. All right, so away from the object and towards the eye. So this is how the image would be seen by the dentist of the object X. So once again, a quick recap is, first you have to locate the image on the other side of the mirror in the same direction, in the same line, and then you draw a line that stretches from the image towards the eye, and in this process you will get a point of incidence on the mirror. Then what you have to do is you have to join the object with the point of incidence using a ray, and the arrows are in such a way that the arrows are always away from the object and towards the eye. All right, then we have some other parts. Let's say for the first one, part A plane mirror produces the image of an object. Describe the position of the object. So for 2 marks we can write image is equidistant with respect to the object from the mirror and on the opposite side of the mirror. And if you want to add this thing, you can also add this one and in the same line as of the object. All right, let's move on to the next one. Then we have state one characteristic of the image formed by the plane mirror other than the position. The upright. So virtual upright, same size. These three are the properties of the image other than its position. The angle of incidence, for which the angle of refraction is 90 degrees. That special kind of angle of incidence is called critical angle. On figure 5.1, mark and label the angle C. So this is a figure 5.1. First of all, before we mark any angle on it, we have to draw a normal. So normal is a line that is perpendicular to the surface and goes from the point of incidence. And it is drawn by a dotted line like this. So let's say this one is representing the normal line, and the angle of incidence would be over here. And that angle of incidence is the critical angle. All right, because it was mentioned in the question over here that angle of incidence equals critical angle of the light in glass. So firstly we draw the normal line, and then we mark the angle of the incident ray with that normal line, and that gives us the critical angle. On figure 5.1, continue the ray of light after it strikes the glass surface at M. So if this angle of incidence is the critical angle, then the light would be refracted at 90 degrees. It would get parallel to the surface, it would get along the surface, or it would get perpendicular to the normal, right? So it would be here, and once again this angle, which is your angle of refraction, this one angle would be 90 degrees. Figure 5.1 shows a second ray of light striking M. This ray has an angle of incidence at M smaller than the critical angle. So if it's not the critical angle smaller than that, then the simple refraction would occur, and the bending of light would be according to the rules. Like if it's bending away from, if the ray of light is entering in a dense medium or in a less dense medium. Figure 5.1 On figure 5.2, continue this ray of light after it strikes the glass surface at M. Alright, so first of all, what you can do is, just for a reference, you can draw a normal once again before you draw any other ray. It's always a good practice to draw the normal. You can just make it a dotted line. Alright, so this is the normal, and what we have to do is we have to bend the ray, because this time the angle of refraction would not be 90 degrees, it would be less than that, and we have to bend the ray away from the normal, because the ray of light enters from a dense medium to less dense medium. So this direction was the actual path. If I bend it to the left side, I'm bending it towards the normal. But whenever the ray of light enters a less dense medium, we have to bend it away from normal. So you can bend it like anywhere on this side. And this one is representing your refracted ray. And the rule of thumb is, I always tell it to my students that they can memorize this thing, D-LAN. Now this one says, whenever you move from dense to less dense, the bending would be away from normal. So dense, D for dense, to less dense, A for away, and N from normal. So DLAN you can keep in your mind whenever we move from a dense medium. And how do we know this was the dense medium? Glass is optically denser than the air. So this one was a glass, and here we have air. Glass is optically denser than air because it slows light more as compared to air. And then we have the next part, part C. The refractive index of the glass is 1.5. A third ray of light enters the block from air with angle of incidence 50 degrees. Calculate the angle of refraction. So for this one, we have a formula. N equals to sine I over sine R. And then what we can do is refractive index is given as 1.5, angle of incidence is given as 50 degrees, divided by sine R as it is. Then we can rearrange it. Sine R equals sine 50 divided by 1.5. Then you can hit it on the calculator. Alright, so once you hit it on the calculator, the value of sine R that you get would be 0.51. But since you don't need to find the value of sine R, rather you need to find the value of sine R only, angle of refraction. So what you have to do is you have to take sine inverse on both sides, and sine inverse of 0.51 would be 31. In two significant figures it would be 31, followed by the unit of the angle, in this case was degrees. Alright, and then we have the next one, number dash question number 5. Figure 5.1 shows a ray of light that enters a semicircular block at A. At B, some of the light is reflected, and some light leaves the glass and travels along the surface. Okay, so what we can see right now is some of the light being reflected over here and portion of light being refracted over here. And in this one, we notice when the light is being refracted, it is being refracted at an angle of 90 degrees. Like here, that angle is 90 degrees. So state the name of the angle of incidence marked 41 degrees. So the angle of incidence for which the angle of refraction becomes 90 degrees, that angle of incidence is called critical angle. So we can write the name of it, critical angle. In other case, if the angle of refraction were not 90 degrees, we would simply call it angle of incidence. Alright, then we have the next one. Alright, rays of light are incident at B at different angles of incidence. In the first case on the left side, on figure 5.2a, the left side one on the left side is figure 5.2a. The angle I is less than 41 degrees. So angle of incidence is less than the critical angle. Draw the path taken by the ray of light at B. If the angle of incidence is less than the critical angle, then the simple normal refraction would occur and the light would bend away from normal in this case, because the ray of light is entering into a less dense medium from a dense medium. All right, so this would be your angle of refraction for the first one. So yeah, this one I can call it R1, the angle of refraction against the angle of incidence I1. Then we have the second case, and in the second case the angle of incidence is greater than 41. And what was 41? That was the critical angle. So our angle of incidence in this case is even greater than the critical angle. And whenever we have a situation like this, if the angle of incidence is greater than the critical angle, plus the ray of light enters from dense to a less dense medium, then total internal reflection takes place. So these two conditions have to be met in order for the total internal reflection to take place. So you have to reflect the light ray in such a way that the angle of reflection equals the angle of incidence. Right, if you're not really sure with it, you can take the help from the protractor. Yeah, so this is your angle of reflection. All right, refraction did not occur here because the angle of incidence was greater than the critical angle, and also because ray of light was entering from a dense medium, which is glass, to a less dense medium, which is air. So that's why total internal reflection occurred. All right, then we have the next one, part C. The speed of light in the glass block is 2.0 into 10 with power 8 meter per second, and that makes sense because speed of light is greatest in vacuum, in space, but whenever there's a medium, it slows down the speed of light, and um, the object that slows down the speed of light a lot, we say that object is more optically dense. So the speed of light we are given with the speed, and the diameter of the glass block is 0.10 meters. So basically meters, that's the value of distance, and we have to calculate the time taken. All right, this thing needs to be calculated. So the standard formula that we have relating these three things is speed equals distance over time. All right, distance is represented by s, speed is represented by v, time is represented by t. Here I can make t the subject, and it would be distance over speed. And then what you have to do is you have to insert the values of speed as well as the value of, sorry, insert the value of, yeah, distance and speed. So the diameter of the glass block is 0.10 meters. Calculate the time as it travels from A to B. So we let's take a look. The light enters the point A, you can call this one point A, and leaves the glass block at point B. For this semicircle, this distance from point A to B would be called radius of this circle or semicircle. That would be the radius. What we are provided with is the diameter of the glass block, of the circular glass block. So what we have to do is we have to convert from diameter into radius, because we have to find the time taken from point A to B, and point A to B, the distance between point A to B represents radius. We are provided with diameter, so we can mathematically convert diameter into radius. So radius equals 0.10 diameter divided by 2. All right, so it would be something like 0.05 meters. That would be your radius, and that is the distance between A and B. So 0.05 divided by the speed was 2 into 10 with power 8, and then we hit it on the calculator. Alright, so the answer that we get for this one is 250 into 10 with power minus 12. Minus 12 seconds. If you want to convert it into standard form, that would be 2.5 into 10 to the power minus 10 seconds. Alright, so basically whatever answer you get from the calculator, you can write it as it is without doing any conversions.